I suspect people will be joining as we get started here. It's my pleasure to introduce Fahd Husain, who's the director of the AI research at Uncharted Software. He actually gave a talk to our AI in agriculture workshop a few months back and did a great job. The reason I was introduced to Fahd, we've never met in person, unfortunately, but he's actually a performer for the World Modelers program, and the director there, Josh Elliott, said that he's an outstanding presenter and really knows what's going on with the World Modelers, and that his team is doing outstanding work. He got his degree from the University of Toronto and from the University of Michigan, and he's been in various data science levels before he was, or data science positions at Uncharted Software before he became the director of AI research. So today he's going to be talking about towards a paradigm for visual modeling, and I guess from there we'll let him take it away. There will be time for questions at the end, I believe, and we can cover those through chat or orally. So Fahd, thank you.
Thank you so much, Seth, for the lovely introduction and the invitation here. Yeah, I will probably stop, I think, halfway through and just take questions as well, because I think it's helpful rather than listen to me ramble on. But today I'm going to be talking about a paradigm for visual modeling. And I do want to sort of outline that even though this is a talk for a data science seminar, this talk is going to cover a lot of different topics. So we're going to talk about system design, we're going to talk about modeling, workflows, methodologies, visualization, some philosophy, and then of course, some data science as well. The outline of the talk is, as you can probably see on the screen, there are three sections. The first is state of the art in philosophy, where I'll go over some of the recent work in visualization and ML. I'm going to talk about what I mean by augmented intelligence, which is sort of our approach at Uncharted. Then we're going to talk about the DARPA programs that this work was developed for, particularly world modelers and automated scientific knowledge extraction. And finally, we'll look at some challenges and we'll try to figure out what a paradigm for visual modeling might even look like. So what is the current state of the art in visualization and machine learning? So recently there's been quite an interest in visualization, but most of the work that at least I'm aware of focuses on visualizing either specific modules or dynamics for machine learning for the purposes of debugging, explainability or interpretability, sometimes even just to increase literacy in current machine learning techniques. There are some AutoML platforms that have emerged, but they're sort of focused on more common problems and sort of machine-assisted workflows for, your usual regression, classification, clustering tasks. So looking at Explainable AI first, which it's mostly around, as I said, debugging, interpretability, and explainability. Right, so you've got three examples on the right here. At the top, you have sort of an unfolded LSTM, which is trying to trace its various activations and trying to figure out how these weights are shifting on the basis of some input sample. In the middle, you have work from Google Brain. This is their What If platform, which allows for, I guess, interactive experimentation. So you can sort of tweak the input parameters and you can see how the output classification actually changes. You can also tweak some of the execution parameters. It's basically sort of an interactive way to do this kind of experimentation. And at the bottom, we've got an example from Microsoft where different data samples that have been classified in positive and negative classes are sort of either clustered together or linked together in terms of their features, or in terms of the threshold boundary and things of that sort, right? But overall, you can see that the emphasis here is typically still on a single model, right? And this model isn't pre-assembled somewhere. And now you're sort of engaging with its dynamics, or you're trying to interrogate it in some way, and you are trying to sometimes debug it in some way. Pedagogically, there's been a lot of interesting work actually that's come out around just increasing machine learning literacy. So you can see the variety of examples here. So the top row are sorts of, I think they're from the same place, but they're sort of examining how GANs actually work, how the distributions for the discriminator and the generator play off each other in competition. On the top right, you can sort of see how a neural net, its activations might move across the network as it tries to classify that spiral space. You can choose different spaces. On the bottom right, you can see the dimensionality reduction, I guess, visual storytelling around it, which is pretty interesting. And in the center, you've got the parameters of Gaussian processes and t-SNE. These are sort of surfaced to users in interactive ways, so people can play with the parameters, see how the algorithm behaves, mostly for just learning purposes. The AutoML systems that I'm sort of describing and which seem to be cropping up these days a lot, they are, they're offered by a lot of the big tech firms, but there are two sort of that I'm highlighting here on the right. The bottom is actually an example from Uncharted itself, and the top is one of our related performers in the DARPA D3M program. The idea here is that we want to try to empower people who are not really experts in machine learning, but sort of walk them through, accelerate them through common machine learning problems like classification, regression, what have you. Here, it's mostly working with the input features, model selection, maybe some model training to some extent, and then examining the output. But these, personally, I find them to be in a little bit of an awkward place because you either have users that require machine learning knowledge to set these parameters or to do model selection, or to understand why a certain model isn't performing the way it's supposed to be, or all of these choices are sort of black boxed away, right? So using various forms of hyperparameter optimization behind the scenes, the users just effectively click run model and they get outputs. And it's arguable how useful that is. So what is our approach against this backdrop, particularly for some of the DARPA projects that I've been talking about? I think it's best understood as a contrast to the current concept of artificial intelligence, which, by the very term artificial, sort of implies that there is there's a contrast to real intelligence, which is human intelligence. And often the goal of artificial intelligence is articulated as an attempt to replicate or capture human skill, right? In my mind, it's better understood more as a geometric intelligence. It has a entirely different ontology. It is not embodied. It lacks intuition and creativity. We've all sort of understand how, even with recent advances in transfer learning, there's a problem with generalization and sort of like synthetical understanding, where a machine can sort of stitch together a lot of different information artifacts to come up with an overall reasoned conclusion. On the other hand, it does have near perfect memory and recall, calculation capacity. It can detect patterns at a scale that is basically inhuman, right? Augmented intelligence, by contrast, which is sort of our approach here, it's a pretty old concept, actually. It dates back to some DARPA visionaries, Engelbert and Licklider, back in, I think, mid-20th century. And the core emphasis here is that we're not trying to replace the human, we're trying to fully keep the human in the middle of the loop, where the human and the machine are actually trying to augment each other by bringing different, I guess, supplementary intelligences to the same sort of interface, right? So this is why it's called a human-machine interface. So we're not trying to replicate human skill, we're trying to technologically amplify human skill. Now, everything is basically a human-machine interface, right? Like the keyboard that I type on is an interface between a human and a machine. But I think it's a helpful concept to have in these times, because while we wait for AGI, and maybe that's going to come in 10 years, maybe it's going to come in 100 years, the paradigm to follow, particularly for problems that are compositional in nature, that don't just have sort of like end-to-end learning solutions like vision or translation, right? Those require human intervention, human synthesis. And so that's why I'm going to talk about visual modeling as a form of this kind of augmented intelligence. So why was all of this inspired in the first place? And it's because we were working on two DARPA programs. The first one is called World Modelers. And here, the goal is to really just model complex systems, particularly social natural complex systems such as drought, famine, and how it relates to food security. Now, modeling complex systems is pretty hard, right? And I think the sort of ambitious goal here of this project is that it's trying to model systems that lie right at the boundary between natural complex systems and social complex systems. You can almost think of it as it's a large natural complex system that has first order relationships with the social system, because the natural complex systems, they have a physics. They are understood models, right? When you move into quantitative social science, then things get fuzzy because human beings are sometimes strange creatures. So we're trying to understand things like causal chains, such as, if rain is lower than expected, how that might impact crop yield. If crop yield is lower, how that might lead to conditions of drought. Drought might lead to famine, and famine might have an impact on food security, for example. But of course, this is a very intricate problem, right? There's systems of systems. The causal dynamics are all over the place. And there's a lot of different types of information involved when you're looking at a system that is this large, right? There's qualitative reports, there's various quantitative models, and there's just a whole host of either sparse data, open source data, high resolution data, and equally lots of different types of models. Most of the models, though, sort of live in their own silos, right? You have political scientists who are very interested in modeling conflict, and that's what they do. You have agricultural scientists who are interested in measuring crop yield, some are measuring flood, and so on and so on. So it's a little bit of a siloed approach. How do we try to bridge them together? The actual problem for world modelers is, it's not just a conceptual exercise, because currently what happens is when a famine event hits, it takes many, many months before aid actually reaches the affected areas, right? You have an event that hits, people then go scour the literature, they build a model, they collect data, they make predictions, they then serve them to policymakers, policymakers decide, they then go to the aid delivery vehicles, then those things are engaged and they are sent out across a road network that is maybe subject to floods. It takes a while, and then sometimes it's as I said, many months before the aid actually gets there. So if we can even just speed up the process or any parts of that process, then we stand to do a fair bit of good. So on the right, you can see sort of the generic model of food insecurity. This is from the original brief that DARPA had put out, right? So you're trying to build these network diagrams, you're trying to parameterize them, and you want to make these qualitative graphical structures quantitative in a way so you can run inference across them again and again and again and simulate various possible outcomes. But how do you do that, right? And to complicate the problem even further, how do you do it visually so that in the interface that you're building, you can hand it off to an analyst, let's say in Ethiopia, where we're doing a fair bit of our work, and they can execute these models to get some sort of crude traction on the problem, right? How can we just help them accelerate and improve their current work, their workflows? So the platform that was developed for this World Modelers project is called Causemos, from Uncharted. And it's basically, you can think of it as sort of an abstraction layer that synthesizes various data, knowledge, and model artifacts. And I'll go into more detail about what this means, but the idea is that you're trying to allow for the exploration of these very large knowledge graphs to extract theories of change, much like the graph that we saw previously. You want to have a variety of data analysis capabilities across different types of open source indicators, high resolution outputs, and you want to allow the user to assemble in iterative and quick ways some computational models or probabilistic models. So this is, I think it's reasonably obvious how all of this sort of lends itself to the notion of augmented intelligence. You're not trying to automate this process, you're not trying to have end-to-end learning, you're trying to enable users to go and stitch together all of these different artifacts in a human-machine interface. So the fundamental, the conceptual schema really that I'm sort of going on and on about is one between data, knowledge, and models, right? So data here can be understood as structured data, spatial outputs from high resolution models, satellite imagery, open source UN indicators, for example, around poverty. Knowledge is a variety of UN reports and documents, an ontology of the concepts in those documents, a knowledge graph of that. And models are when you sort of combine data and knowledge together, you can have these single model workflows where you can parameterize and execute these things. You can do intervention analysis and so on. The overall structure of the World Modelers program, just to give you an idea, it's quite large, right? There are about 20 or 30 teams, and all of them are involved on one aspect of the problem, right? So if you sort of look at the yellow chunk of this diagram, that's the knowledge part, right? There you have readers that are looking at UN reports, NGO literature, news reports, and so on, and they're just reading all of these at scale. Right? These are then passed forward to an assembler, and this assembler reads for causal assertions. I'll describe that in a bit. And it effectively extracts a knowledge graph out of those documents, which then gets passed forward to Causemos. In the purple, you've got people producing all sorts of data, right? You've got indicators, people are trying to find them from the internet. You've got spatial output that's being generated by either satellite imagery or machine learning on satellite imagery, or just, I guess, spatial models. And then all of those are sort of housed under these graphical structures that are then run against engines, right? And by engines here, I mean inference engines that sort of convert these graphical structures into Bayes nets and really simple Boolean networks and so on. So on the left, you can sort of see an example of the Causemos interface looking at a particular document, right? So that document gets converted into something like on the right. And there the idea is that there's a bit of text at the very bottom of this diagram. That text was identified as something that had a causal assertion that was embedded in it. Right? The factors in that statement, like conflict and food production, are then extracted as an example of a causal statement. Right? So conflict has some sort of negative relationship to food production. So that's one sentence. Now imagine we're doing that for hundreds of sentences, right? And each of those factors are then mapped onto a concept in a governing ontology. So here, fighting and conflict, for example, are mapped onto violence, and wheat yield and food production and so on are mapped onto food security. Why is this happening? Well, from a modeling perspective, it's machine extraction at scale is pretty noisy. But we're hoping that if you can aggregate all of these extracted causal statements, you will be able to have some notion of the higher order structure of relationships that are possible in your corpus. So you can think of the resulting knowledge graph, which looks like that on the left, as an expression of all of the causal hypotheses that have been asserted by human beings in the document, right? So the actual interface, which is on the left, you can sort of see that in the middle of it, you've got I guess a small section of the knowledge graph. The graph itself is massive. The nested boxes, which you can see, they are actually the hierarchy of the ontology, right? So each leaf node is nested in a box with its parents, and that's nested in further boxes and so on and so on. On the left, you've got various attributes of this information. So you can filter, you can facet, and you can search amongst it. And just on the right of that main image, you've got a drill down. So now we're looking at the evidence pieces underneath the drought and road axis. Why is this relationship there? What snippets of text are informing this relationship? And just how much confidence do I have that this exists? So a typical workflow would sort of explore this space. Then it would go to the top right, where they would extract a subgraph of interest, right? I mean, you want to model certain things, and you have a sort of candidate template that is a subgraph, and you want to try and go from a qualitative space to a quantitative space and turn that subgraph into something computational, even just for the sake of like semi-quantitative inference. At the bottom, on the bottom right, you have an example of that same subgraph. It's now just rendered vertically as an arc diagram. So each circle still represents a concept in the ontology, but then that concept is attached to an indicator or some other low-level data source, right? You can sort of see those in the gray sort of time series. This is then fed to an engine, so you can think of this in terms of a BaseNet, where the concepts are latent variables and the time series are observables. And using the observables, you can kind of parameterize the BaseNet to do inference, right? And on the very right, you sort of see how the dynamics of the model are evolving as you push the entire model forward. So I've got a little video here for a few minutes. This is something that we put together a little while ago. So I'll just let it play for a bit. But you know, actually I can sort of flip ahead. So there's a first aspect of just doing this kind of contextual analysis for the knowledge that's present, right? You have a lot of different views on that knowledge. You want to be able to see where this knowledge is distributed. So these documents and statements are coming from all over, right? You want to be able to zoom in and interact with it. You want to be able to select certain parts either interactively or through a search bar at the top. And you've got various facets on the left that you can also use to filter, right? Oops. How did I do that? I'm sorry. Here we go. Yeah. These are documents that are, as I was showing previously, they were sort of collected. This leads into qualitative modeling, where the actual documents and the number of statements are expressed as this sort of hierarchical ontological graph. There are a variety of layout options that you can use to sort of organize the knowledge a little bit better. But effectively, this expresses the causal hypotheses that were present between economic crisis and livelihood and food consumption, and currency devaluation, all of the concepts that had grounding in the literature that was addressed, right? If you select an edge, you end up with evidence pieces on the right, as I've described before. To let this play through. You have the ability to curate actions, which is an interesting concept, because when you read things at scale, you really end up with a fair bit of noise. But a human being can easily sort of see if a certain relationship doesn't make sense, particularly if they've got some knowledge, and they can engage in a curation action and change the polarity of a relationship or change the way that a factor was mapped onto a given concept. We're sort of working on recommendation systems built around that. So if a human being sort of engages in a single curation action, how we can sort of amplify that to suggest recommended actions across the knowledge graph. So now here we selected a subgraph of interest, and we decided to move forward with analysis. We've created that, and then we move forward. Here's a bunch of different models that have been created in the past. So some of these came from some of our users in Ethiopia. The idea here was to try and present a multi-model space where you can sort of look at models structurally and do some kind of comparisons, see which ones are, which concepts are common, and if you have common concepts, what are the common structures? This is just sort of the very beginnings of trying to just do sort of like multi-model analysis, really. From here, you would sort of select a single model. The stuff that's being highlighted are the indicators that you use to ground each concept, right? And you have the ability to sort of drill down further into the indicators and engage in like aggregation options or selection options of some kind. Maybe select a certain time series of interest. Maybe explore other indicators that might be good matches, right? We also have the option to ground nodes in really high resolution spatial output, right? So this is output that's coming from some other modelers in the program, and you can use that to sort of parameterize these nets in some ways. Right now here, you're seeing examples of interventions where a user sort of goes in and says, I'm going to raise this node artificially because I know that so-and-so event is going to happen, or I like to speculate what is and is not going to happen if I would sort of intervene here. This is the same graph just expressed as a flow diagram because that arc view is useful for parameterization, but not really for trying to understand causal dynamics across, right? And then you can just, share these things. You can publish them, you can download them, and whatnot. So there's another, I've been talking about high resolution outputs here, right? And at some point, there were a fair bit that were being produced by a lot of modeling teams. And so we ended up building sort of a data section of the application right here. And the idea here is that, it's not necessary that every analyst that's using Causemos wants to build that semi-quantitative or crude inference model in terms of causal analysis. Sometimes they just want to do sort of like ArcGIS style investigations and algebraic queries across these different outputs. So here you can sort of see that there's, I think, 6 or 7 different outputs from different models, and the analyst here is trying to understand for a range of values for one output, what are those how does that range correlate with other outputs that are also present in that region. So here you might want to think about the sort of answering these like complex, I guess, compositional questions such as, tell me which areas are under a high risk of flooding, have high population, have low wealth, and have some notion of rainfall or drought, right? And previously it would be a pretty manual process, but we're trying to sort of empower that. The idea then would also be to sort of like build almost like composites of these indicators, and then sort of these outputs, and then use them as indicators to ground some of the qualitative models. These are just sort of experiments in trying to, I guess, trying to visually render some of these very, very large outputs very quickly, because these things are, there are dozens upon dozens upon dozens of them, and you really have to enable the user to do this seamlessly and not like wait every single time. So we're not just doing this for the sake of research, right? So like as I mentioned, we've had a lot of engagement with the particular Ethiopian users. The current use case is centered around food security. We have some stakeholders that are either academics or modelers or consultants in this space. And with support from the Bill and Melinda Gates Foundation and Luma Consulting, we have had them use the system multiple times. We've gotten a lot of positive feedback and a lot of criticisms. I think the system itself is about 2 years old, and there's still at least 2 years left of development and research. So if it's consistent engagement with them, try and see how what we're building actually amplifies their workflows, what sort of features they'd like. Once again, it's this like sort of augmented intelligence approach where the human being sort of is driving a lot of this. There's a bunch of R&D that is coming up, I would say, in the next 6 months or so. So there's a variety of, on the top right, you can see that the number of documents that are now being ingested are exploding, right? So you've got hundreds and thousands of them that are sort of coming in, and that space has to be understood well. You can't just show hundreds and thousands of documents in a flat list. So now we're looking at notions of hierarchical clustering to try and understand how that might just allow the user to browse that document space a little bit better. On the bottom left, you can see like more nuanced views for that data exploration space that I was talking about. And on the right, just because as the knowledge and the data gets larger, so do the graphs, right? So in the middle, you've got an example of, let's say, a small toy problem in some of our new design, but at the bottom you have an example of some of these really hairy, huge graphs, right? That a user can easily build in 5 to 10 minutes. Do we want to enable that? To what degree? How do we make sure that they're not spinning around in circles? It's a pretty complex thing. I thought at this point I might just stop for a couple of questions because before we get into the next program. I know that there's a fair bit of content there, but perhaps we could take a question or two.
So it's probably best if people put questions in the chat, but if anybody would like to unmute, feel free to.
Sure.
I mean, I guess while we're waiting here, I've got a bunch of questions, but one of them is you showed a map, and you talked about placing the data as to where it's coming from. Is that based on some type of geotag, or is that based on information within the document, or how is that figured out?
A bit of both, actually. Like some documents, or I'm trying to find it actually. I think you mean something like that, but it was I think during the video. It's some documents explicitly reference which factors are present where, right? Because what we're really trying to do is not place the documents at in the map. We're trying to place these events, right, or these factors in the map, right? So if there's conflict happening, where is it happening, right? If there's a food security shortage, where is that happening, right? It's less interesting to know where the document came from, but more interesting to know where the entities in that document are placed spatially, right? Because often you'll have food security events in a variety of places, right? And you really want to try to understand and focus on only the ones that are relevant to your local analysis. Does that make sense?
Yeah, it makes sense. I guess I've been talking to Phil Root and some of the other folks at DARPA, and there's questions on, you know, intentional bad actors. And, you know, I could imagine somebody could place information that's misleading on purpose into the system. That's why I was sort of curious where it was coming from.
Yeah, I think at the very first step, we have ways to filter out information from certain sources, right? So if I sort of know that a document is coming from a news source or some agency that I don't have a lot of trust in, then I could filter that out. Or alternatively, I could filter only on that and try and compare how that information relates to information coming from other sources, right? It's interesting because we're reading at scale across a large amount of sources, and by we, I mean the whole program, you end up having a lot of redundancy in claims that are truthful, right? Because they're just sort of present across a variety of different sources and platforms. And if you see that there is a lot of redundancy in a claim that's coming from a single source, right, then it's probably an amplification of some kind, right? Which you probably want to be skeptical about a little bit. Does that make sense?
Yes, yeah. You got two other questions here. Alexander Sun asks, how do you differentiate between causal and correlation in your graph analysis?
Yeah, this is a question that comes up every time, and the answer currently is not very well, because eventually what we want to do, I mean, right now we've sort of been focusing on building almost the visual skeleton of this interface, but really what we want to do is introduce almost like causal checks that come in when you are extracting the subgraphs. So you can't do the sort of like Judea Pearl do calculus checks at the scale of the whole graph, right? That's just impractical. But once you've isolated certain subgraphs of interest and you really want to try to model with them and try to like parameterize them and so on, that's the point where I think some notion of causal analysis and checking can come in and help you identify where the confounders are, which relationships are not actually causal, and that would inform how you go ahead and assemble the model. But right now, I think this is why when I speak of these links, I talk about them as causal assertions in the sense that they were asserted by human beings in some documents. It's a hypothesis, right, between A and B. And eventually we can sort of see this as just a collection of causal hypotheses that have yet to be validated in some way. So all that to say is future research. That's the last two words on the slide here as well.
Great. Justin Helk says, what role does qualitative context play in helping to determine causation?
Yeah, so it's in helping to determine causation, I think it's a bit of a tricky question. So first, just looking at information qualitatively, right? Just looking at the knowledge graphs, trying to understand the ontology, trying to understand how various concepts are linked. That's really powerful, right? Because you have people that come in, these are experts in food security. They have read, 20 papers in the past week, and they've retained some information, and they've got a notion of a mental model in their heads which is like qualitative in some way. It just looks like a node link diagram. But when you sort of throw those concepts in that diagram into the whole knowledge graph, they end up seeing all sorts of interrelationships that have been proposed in some way by the documents, right? So it allows them to find surprising connections or connections that are valid in certain contexts, depending on how you filter the original documents. And that allows them to sort of expand their models, to complexify their models, and just like allows for a certain amount of surprise. So that has been something that they've really, really appreciated, which is just sort of like a high level awareness of all of the different possible hypotheses that were encoded in the documents. How that infects causation, it's the same answer as the one before, which is that we have to do a better job when we're extracting subgraphs, which are at that point still qualitative, right? At that point, we have to say, well, I've done my causal checking. Here's a variety of confounders and relationships that do not, in fact, subscribe to causality. Are there any other paths in the background graph that may be included, right? That may actually have those causal semantics that I'm looking for. So it's sort of this is like tearing between a subgraph and a larger knowledge graph, if that makes any sense.
So just to follow up on that, is that the same as, say, in terms of statistical modeling, a global calibration versus a local calibration? You sort of drill down.
I would think, yeah, I would think so. So it's very hard to globally calibrate across, I don't know, hundreds and thousands of edges, right, in a giant hairball, right? So the graph that you're seeing on the bottom right here is just a small subset, right, of the whole thing, right? So global algorithmic checking is going to be difficult, right? Unless we come up with incredibly efficient ways. So it would be mostly local, but I like to see it as like sort of local plus plus, which is local and it's, let's say it's immediate neighborhood or a neighborhood that satisfies some constraints, right? It's not going to get you to global, but at least it's going to sort of examine the various interrelationships and the neighborhoods around the concepts of interest, right? It's still not global though, but yeah.
So those are the questions that people typed in. I don't know if anybody would like to unmute or if you want to keep on going.
I can keep on going. Let's save the rest for the end. So the second program for DARPA that we're sort of working on that's quite related to for modelers, and it's something that we've just kicked off, I think about last month or something, is around the pandemic and COVID-19. So the issue here is that I think for one of the first few times in scientific history, all scientific research around this phenomena or not all, but at least a lot of it, is just open, and everyone is sort of chucking models and papers and data across various national boundaries. And you would think that this would be a good thing, but actually people are sort of drowning in this sort of information, right? Particularly because a lot of these epidemiological models they have different representations. They're really hard to understand. You have to trace their author, you have to trace it back to their authors. You have to call up the Imperial College in London and say, why did you set this parameter to be this way? There's a lot of uncertainty around. These models don't really have any provenance or metadata. And then there's this weird standoff now that we've got between immediate action is required around a lot of these COVID problems, but there's a very large sense of model fatigue. Like you don't really know what to do with all of these different models doing, just making all sorts of wild predictions. You also have these like sort of comical cases where you've got physicists or mathematicians or people who are generally quantitative in some way, either build a neural net model or some kind of epidemiological model, and they predict, and it seems like half of North America is going to die in a month, and then others where it's really not going to have much of an impact. How do you trust those two predictions? How do you even try to interrogate those? I think the whole point of this program, at least for now, is that we're trying to allow for some sort of like visual modeling or augmented intelligence platform where some of these models can be brought together and examined in common ways. So here, as I was just saying, the idea would be to sort of increase usability and transparency of these diverse model artifacts. You want to really go from a single model workflow, which is the stuff that I was talking about before, right? I mean, you're going from all of these data and knowledge artifacts to create these single models and then do inference on them. You want to go from that single model workflow to a multi-model space, maybe even a meta model space, because really you want to be able to compare the different variants of epidemiological models, either structurally or parametrically or in terms of output, right? You want to make sure, once again, that all of these model representations are linked back to some source knowledge, either code bases or the papers that they come from. And typically, in sort of the spirit of complex systems, you want to talk about these models as these nested systems, right? We also, I think, to sort of move forward with some of our spatial view, I think COVID is essentially a spatial phenomena, right? And we have a fair bit of spatial models that are trying to predict, how the disease might spread in hyper-local environments, right? So if it's present in a neighborhood and traffic of humans is going from one place to the other and mobility is high, right? How might the disease actually spread across, which you can imagine is something like a spatial network. That's further on. So the schema previously has sort of been extended into experiments as well, right? But for now, we're sort of focusing on the knowledge and models part, right? Which is that we really want to try to get common representations of the models, and we want to be able to link them back to knowledge. So again, I don't have to call up the scientists in Australia to understand their model, but I've got some notion, some general representation of a model and some relationship to its source code or its papers and metadata that's sort of present. And I can engage with it in some way to even just accelerate this sort of stuff. So one of the things that we're sort of doing that's coming from our models as well is that models we're now just casting them as graphical models, different types of graphical models, right? So there are the sort of node link diagrams that you saw previously, but now we're also considering computational graphs on the right. That's a convolutional net in TensorBoard. We're also looking at probabilistic graphical models of the sort that were there before. But of course, there are issues, right? As soon as you open up the door to different model representations. First of all, these things are systems of systems of systems, right? They're all nested and interconnected in different ways. All of these have different semantics for the nodes and the links, right? If you want to visualize one in a certain way and effectively build interactions on that visualization, how do those interactions and the semantics of that visualization remain consistent for the other representations, right? It's a hard problem. So to just start, we're going to take some very simple node link representations and try to just enrich them according to very common sort of attributes, right? Because again, we'll have dozens and dozens of models, and we want to at least make them interactive and visualizable, right? So we've got node attributes, we've got link attributes, and we've got group attributes. And the idea would be that we're trying to find a common semantics across these, and we've got some help from some of our performers who've actually done a lot of work in formal analysis of the models and how one model representation can be cast into another or can be cast into intermediate formats that sort of are the junction of various model representations. So we're trying to sort of work with them to understand what exactly would be helpful here. As I was saying before, the idea is eventually, not just to have a good single model representation. The idea is to look at multi-model space, right? And so the first thing that you can do is to start to compare in a common representation, start to compare multiple versions of the same model, right? Or to try and compare different models structurally, right? How do a virus in a population in one epidemiological model, what is the relationship there does it have any confounders? Does it have any circular relationships? Does it sort of take an indirect path to get to it? Are there gates in the middle? So on and so on. And how does that relate to this other model representation, right? These are all like visual and juxtaposition questions to start with. This would be sort of like structural analysis first. Then we would sort of get into parametric analysis, right? And say, well, I've got 2 or 3 different models. Within what parameter ranges across these models do they all converge in the same output, right? You can also sort of think of it in a slightly different way, which is like, how can we ensemble these models, right? If you've got a bunch of different classifiers, how do we sort of make them a supermodel in some way, right? There's this notion of having a model cast against background knowledge is going to be important, right? We've sort of understood that a model is sort of extracted from a background graph of interest, right? And that's just critical, basically, right? Hierarchical models are something that I've been going on about, and that's because each model can be decomposed into lots of different systems, but also that various models exist at different levels, right? So you've got biological models that are working at the molecular level. How do they interact with models that are working at the population level, right? This is a very hard problem, and I don't think we're going to solve it, but I think that there are just like relationships here that can be articulated, maybe. I think the idea is to sort of consider both of them first and see how exactly information could flow. So some of the prototypes and designs that we're talking about are sort of computational graphs on the right, and you can see some of the design artifacts on the bottom, right? We're sort of working with the same sort of highly interactive, highly scalable sort of representations, lots of collapsing, lots of interactions, drill down, and context backgrounding. That is also possible. Finally, we sort of have to deal with the problem that some of these graphs are very, very large, particularly when you're talking about biological models. So you have to start to really work with these hyper-performant and almost high-dimensional visualization techniques that allow you to work almost like do this sort of like hierarchical clustering that allows you to look at larger subsystems and then decompose them into smaller and smaller and smaller subsystems. This is also very important just because of the scale of the data that we're working with, particularly on the molecular side of things. So what does all this mean, right? I feel like you can kind of understand some of the common themes that I've been going on about in this little while, but I'll just articulate it a little bit more formally to sort of end this talk. But the first is a couple of challenges keep coming up in these kind of systems. And the first is that users are resistant to change because they are sort of they're sort of enamored with the existing technology that they have, and they are sort of tied to the contours and the limitations of their workflows. There's also the second point is that users carry a lot of expert and prior knowledge. So we can't have a system that is sort of closed off, right? That's sort of like an end-to-end system where you put an input and you get out output and you just sort of examine the output. You have to be able to allow the user to encode their expert knowledge with their priors into modeling itself, right? This makes it a bit complicated from a design perspective, from a modeling perspective, from an engineering perspective. And you've got lots of different types of users, right? Some of them build things, some of them tweak things, some of them just want to consume the output. Again, all of this requires a certain amount of design flexibility. A thing that really helps users is a lot of metadata, but particularly in sort of the COVID cases I was alluding to, metadata for scientific knowledge is not an easy thing to get, right? Descriptions, parameter interpretations, what does good output look like? This is mostly a manual logging process, right? So until we have more automated ways of doing that, and some of the ASKE program is trying to encode that manually through code reading and the identification of certain aspects of papers, until we can do that, knowledge is a little bit hindered there, right? So we're still trying to figure that out. Other sets of challenges are even when we are articulated with just models that can be cast graphically, they're still, the common forms are still hard, right? Even at an API level, node link objects get pretty complicated. They're quickly enriched with various expectations. At the visual representation level, the semantics are not aligned often. And if you have interactions that are based on some semantics, and those become inconsistent across models, right? Empowering a user, this is sort of the second point. The more you empower a user, the more you make a process somewhat subjective to their choices. And the uncertainty sort of compounds at each step of the workflow, right? So that it just means that we have to have a notion of how this kind of uncertainty is captured for every user decision in the modeling process, right? To make sense of any data at all, right? Particularly data at the scale, we're going to need hierarchies and aggregations, but these are often imposed on by the visual system, and they're not typically a good fit. Sometimes they lack proper coverage. Sometimes they don't have the right resolution to smooth things out too much. And finally, of course, engineering a platform that spans this like network of interconnected services where each is trying to solve basically an unsolved problem with a research agenda, it's hard. So just to sort of like wrap up, I kind of wanted to talk a little bit about some of the core things that we've sort of extracted along some of the axes of what visual modeling might look like, right? So from a representation perspective, right? We want to try to cast all models as graphical models of a few core types, right? We don't want to just have an explosion of representations for all of the reasons that I was talking about before, right? Those would probably be computational graphs, wiring diagrams, and node link graphs, right? We haven't seen cases where the sorts of models we want to engage with would fall outside of those, right? Or couldn't at least be translated into those in some way. The core model components would be nodes, edges, and groups and combinations, right? Like hypernodes, hyperedges, things like that. And the different semantics, of course, needs to be possible. The difficult problem is trying to maintain the abstraction sweet spot, right? Where as the models grow, your generalized representation has to be able to span it, but the structure has to be flexible enough that you are sort of capturing the critical pieces of each model. And that's always sort of like an ongoing exercise, really. In terms of users and workflows, the whole point of visual modeling is that you're sort of engaging in multi-domain and multi-model space. So even modelers who have expertise in a single domain, they immediately become general modelers as soon as you throw them into a space where there are models from a lot of different places. As I said before, there's a non-linear workflows that need to be iterative. You have to allow the user to jump between different spaces to pick up knowledge artifacts, data artifacts, stitch them together in different ways, right? Because that's just the way that users think. I'm building a model, suddenly I remember, oh, there was an indicator that I can use. Maybe I should explore a relationship here, and so on and so on, right? But the trick here is that as you increase that capability to bounce around, right? The different spaces, I often, as a modeler, I end up building things that I don't remember how I got there. So if I build a model on Tuesday and I come back next Tuesday, what are the decisions that led to that model, right? Or even that analysis. So provenance and bookmarking and annotation become very important very quickly, because otherwise you just sort of have a bunch of final model artifacts and you have no idea what would happen there. How does machine learning sort of play into this? It's because user interactions are sort of full of implicit and explicit cues, right? Like they're exploring a certain space of interest. You need sort of machine intelligence suggestions and machine assisted guidance to help the user to explore that space, but you have to be able to try and figure out these clues so that, for example, if I'm exploring a subgraph of a certain kind, the machine is going to sort of surface recommendations that are relevant to that graph and not from other places. These services have to be lightweight, obviously, because they're happening in real time. They have to be tweakable to an extent, and they have to be developed with active learning in mind, because there is a lot of user input and there's a lot of user engagement. And if you have sort of checks at different parts of the workflow, you can actually capture that feedback and use it to tune the algorithms in sort of like an active learning paradigm. Of course, all of this presupposes that you have interpretation and transparency and the usual sorts of problems that users have with models. But thankfully, all of the work that I sort of introduced in the beginning, we can borrow from those concepts a lot. That's what current visualization research is. And just a couple more things. Linking and abstraction is going to be pretty important, as I've sort of repeated over and over now. You need some kind of conceptual organization for the knowledge pieces, for the data pieces. You need things like hierarchical clustering and data summaries. You need principles of effectively progressive disclosure. I find some higher level concept. I interrogate its children. I explore that to the next level. I find a single piece. I want to understand that. You can see sort of this chain going, sort of moving up, moving down from the top of a sort of abstraction hierarchy. There's this constant tearing between background and foreground, between high level and granular. So linked views and linked artifacts are pretty much central. And that sort of leads into how every artifact has to sort of be contextualized with the other artifacts. Models against knowledge, data against models, knowledge against data, right? There's all of these relationships in between that will guide the user to build that kind of cohesive understanding. So in summary, what does something like a visual modeling paradigm look like? And the idea would be that it's something that allows general modelers to move through various stages of a modeling workflow interactively, iteratively, and visually, right? The capabilities here should be, they can either engage or assemble diverse model representations, right? Not from their own domain, but from other domains as well. They should have access to knowledge and data and be able to explore those two spaces separately as well. And it should allow for like single model perspectives and meta modeling perspectives. And then to top it all off, you have to do all this visually, right? The core components here would be the stuff that I've mentioned: graphical modeling, knowledge contextualization, abstraction hierarchies, linked artifacts, nonlinear workflows, and of course, the user is always in the loop. The benefits here are it increases the speed of iteration. There's a lot of synthesis of information that the user and the system can do together. There's general visual forms of models hopefully allow for broader engagement and allow you to engage with different aspects of the compositional problem too, because you can look at the problem from all of these different perspectives, visually, from a data perspective, from a knowledge perspective, from different model output perspectives. It is clearly a very interdisciplinary paradigm, right? If you've got machine learning systems, they have typically a heavy emphasis on engineering and a heavy emphasis on model development. Maybe they have a small UI on the top, but this is, you need a lot of conceptual work, almost philosophical work. You need design work, you need consistent engagement with users, interaction, workflows, engineering, visualization, and so on and so forth, and then finally you modeling as well. This is just sort of to close out. This is just the beginning of our journey, really. There's a lot of research to come and a lot of synthesis of all of these different threads to come to fully really articulate what we think is a paradigm of visual modeling. So that's about it. Thank you very much. And I do want to give some shout outs to some people, both internally and externally. And if anyone's interested in all of the different bits and bobs that I've referenced, they're all over here.
Great. Well, thank you very much, Fahd. I've